Alright guys, this is going to be kind of a long video because I'm doing a lot of stuff in one. So this is 11.2 and 11.3. The 11.2 part's going to be pretty short. Okay. So in 11.2, all they're really asking you to do is compare linear and quadratic functions. So the first few ask you to look at a graph. So for example, here is some data, and then you graph it, and you just it's not any harder than this, guys. Did it graph in a straight line or did it graph in a parabola? Okay, so that one graphed in a straight line, so that's linear. All right, number 2 also graphed in a straight line. Number 3 graphed as a parabola. So clearly that's quadratic. Okay, so that's that part of the assignment. The next part of the assignment wants you to use a strategy. If you don't have graph paper, if you can't take that data and graph it and you want to know if it's linear or quadratic, yeah, you could put it in your L1 and your L2 and turn your scatter plot on and look at it. You could, but this is frankly shorter to do. Okay, basically what you're going to look for is, does the data have a consistent rate of change on the first try? So what I mean by that is looking at the y values. -6 to -3, well, that went up by 3. -3 to 0 went up by 3. 0 to 3 went up by 3. In fact, we're going up by 3 every time, and it worked on the first try. They show doing it again, like 3 minus 3 is 0, 3 plus 0 is 3, 3 plus 0 is 3. If you get, what you're really looking for is, does the difference come out the same number every time? If it is, that's going to be a linear function. Okay? Well, what happens if you have something like number 8? Like 12 to 3 went down by 9. 3 to 0 went down by 3. So we're going down by a different number this time. 0 up to 3. Now we're going up by 3. And 3 to 12, we're going up by 9. So that's clearly not the same number every time, and when it's not the same number every time, that's when we start to know, well, it's not linear. Okay, I can't tell at this point if it's quadratic or exponential or whatever, but I definitely know it's not linear. Okay, so then I start doing the exact same thing again. -9 to -3, well, that went up by 6. -3 to +3, well, that went up by 6. 3 to 9. Oh, that went up by 6. So by the time we get to the second column of doing that, then I do have the same number showing up every time, and that tells me that this is quadratic. Now, it's not going to happen on your homework, but if for some reason you were doing this on a problem on the Regents or something, and it didn't, even on the second try, you didn't get the same number every time, then you know this is not linear, it is not quadratic, it's something else. It may be exponential, it may be absolute value, it may be something else, but it's not linear or quadratic. And at that point, I would encourage you to put it in your L1 and L2, look at it on your scatter plot, and make that determination. But for your homework, it's either going to be linear or quadratic, one of the two. Now we're going to get into 11.3. Okay, and the way I taught this in class, I went out of order. So we're going to fast forward a little bit. Okay, on page 641, I started off this lesson by talking about interval notation. So interval notation is when we're talking about an interval on a graph. Okay, we're talking about like a certain portion of the x-axis or a certain portion of maybe the y-axis or something. And previously we could have written like a compound inequality, like x is, x is greater than 2 but less than or equal to 10. Okay, and what interval notation is an even shorter way of writing that. Okay, you start with a comma and that's in the middle. Then the smaller number goes on the left, the larger number goes on the right, and then brackets. If there's no equal, or it doesn't say the word equal, or you know logically it can't be equal, you put a round bracket. If it has an equal bar, you read the word equal, you know logically it can be equal, you put a square bracket. Okay, so there's that. It doesn't have to be a compound inequality. If I said that x is greater than or equal to 7, okay? Now, you have to think about this logically for a minute, because what you have to do is place the 7 correctly first. Is 7 the largest possible number or the smallest possible number? So 7, if x is greater than 7, then 7 is the smallest that it can be, and x is going to be bigger than that. So 7 is going to go here with a square bracket. Okay, well, Mrs. Andrews, you said it has to have 2 numbers in it, so there's not a second number. Okay, well, x greater than 7 means any number bigger than 7, which goes to literally infinity. So we use that sideways kind of 8 shape for infinity, and infinities always get a round parenthesis. Okay? What if I said that x is less than 20? Okay, so x is less than 20, therefore 20 is the biggest number it can possibly be, and x has to be less than that. So the 20 is going to go on the side of the comma where we're talking about the largest number. There's also no equal bar, so 20 gets a round bracket. Here again, since I don't have another number and it just says x is less than 20, that means we're going to infinity. But we're going in the direction of going down. That negative in front of the infinity does not mean only negative numbers. It means we're going down to infinity. And again, infinity always gets a round bracket. Okay, so then we looked at a couple homework problems. So here's the first example. This is number 7 in the 11-3 packet. It says all real numbers greater than or equal to -3 but less than 5. Okay, so -3 is the smaller number and 5 is the larger number. They're separated by a comma, and because it said equal, then the 3 got the square bracket. The 5 did not say equal, so that got a round bracket. Here's another infinity one. All real numbers greater than or equal to -100. Now, some students found it helpful to write that greater than or equal to -100. Some students felt if they wrote it as an inequality first, then they converted it over to the interval, then they found that helpful. Okay? Here's the next one. Okay, greater than -36, smaller number, less than or equal to 14, larger number. Letters, all real numbers less than or equal to b. So that means b is the largest it can be and everything else is smaller. And again, we put that negative sign in front of the infinity to say that we're talking from, the smallest, you're getting smaller from b as our high point. Okay, so there's a couple examples from that section of the homework. Okay. The next thing that I did when I taught this lesson is we did practice some of our vocabulary. Okay, vertex, which in a parabola is that point down here where the parabola turns. This is the vertex right here. And the vertex in this parabola is a minimum because it is the lowest point. So you can see that I have additional things that the directions don't tell you that I have had my students do. Okay, so I want you to tell me what the vertex is and whether it's a minimum or a maximum. So the vertex here is a minimum, and the coordinates of that are -3 and -9. I also had you look for the y-intercept right here. X-intercepts. In this, a parabola can cross the x-axis twice, once, or not at all. In this particular picture, it crosses twice. I get one here at the y-intercept, which is a coincidence that the y-intercept and the x-intercept are the same point, and over here at -6, 0 as well. So I put those also. The word zeros is a synonym for x-intercepts. So please know that vocabulary word, know that those words are interchangeable. Okay? And every time we've talked about a function, we've always discussed its domain and range. In a parabola or a quadratic function, the domain is always all real x. And just for fun, we practiced writing our interval notation. So the domain in interval notation is -infinity to +infinity. Every x value is okay to use in a quadratic. Okay? Now the range is related to your y value in your vertex. The vertex is the turning point. So the range here is -9 to +infinity, or all real y greater than -9. If I look at the y-axis in this picture, the graph is passing by all the y values until we hit -9, and then anything below -9, the parabola has turned around and it's not going to pass those points. Okay, so I want you to do that. The other thing that I'm having you guys do in 13 and 14 is interval of increase and interval of decrease, and that is officially what the directions tell you to do. Okay, and I'm going to move my graph out of the way to demonstrate this, just so it's not too cluttered. Okay, in class and on this video as well, I'm going to do this with a highlighter because it helps demonstrate things. Okay, so in this picture, interval of increase, I think we can agree if we look at a parabola, in this section of the graph it's decreasing, then at the vertex it turns, and now it is increasing. So here's how the color coding works. I recommend you have 2 color coding. Increasing and decreasing, you read a graph from left to right, okay? And the point where the graph changes direction is the vertex. So I had you in class go to the vertex, follow it up to the x-axis, and then highlight the x-axis in 2 different colors. Okay? Now, the x value right here is -3. And then this is to -infinity, and this is to +infinity. All right? So on this side of the graph, the yellow side, in this problem, it's not every problem, in this problem, this is where the decrease is. So you can see in their answer, interval of decrease is from -infinity to -3. Now, we already knew that infinities get round brackets, but you'll notice -3 also gets a round bracket. And it's not because x can't be -3. It absolutely can be. Okay? But this isn't about domain and range. -3 is the vertex. It is the point in the parabola where it is not increasing and it is not decreasing. It is the only point in the graph where it's not doing either one. It's that moment of flatness. Okay? So that's why that gets a round bracket, is because it's not increasing or decreasing at that point. All right? This side is where we are increasing. So that's why my interval is -3 to positive infinity. And again, both of those get round parentheses around that. Okay, so for 13 through the end of 11.3, you're doing the interval of increase and decrease as I've just demonstrated, but you're also finding these other things that you can easily see on the graph. Now, I do want to look at this one. Okay, number 15. Okay, so number 15, you can see that I put the vertex. Here's the vertex, which is a maximum because that's the high point. I have this y-intercept here. X-intercepts, just by coincidence, this is also an x-intercept. Here's an x-intercept, so those are labeled. -2. Oh, wait a second, that's a total lie. I have to pause for a second. There's my y-intercept. Okay, my y-intercept actually appears 0, 8. I'm standing very close to the screen and it threw me for a second. Okay, -2 and 0 and 4 and 0. Those are my x-intercepts, also known as my zeros. Again, the domain of every quadratic is all real x. Okay? The range of a quadratic is related to, see the 9 here, is related to the vertex. Okay? So the range is going to be real y less than 9 because this parabola opens down. Or we can write it as -infinity to 9. Okay? Let's talk about interval of increase and decrease. Let me erase some of this. Okay. Interval of increase and decrease. Again, find that vertex, come down to the x-axis, and I highly encourage you to color code. Okay. So this is +1. This is -infinity. This is positive infinity. Okay? And at this point in the graph on the yellow side, so this is different than the other one as far as increasing or decreasing because this parabola opens down. So this side is the side that is increasing. So my interval of increase is -infinity to 1 with round parentheses. Okay? 1 is the highest number of x value during the increasing portion. And then my interval of decrease, this is the part of my graph that's decreasing. Okay, is 1 to positive infinity. And you might rightly notice that 1 and 1 are opposite each other. Infinity and -infinity are opposite each other. Okay, that should always happen. Okay, so that is that part of the homework. Then there's this part. Okay. I'm going to need to pause it to get this set up the way I want. Okay, I'm going to start fresh with problem 2 instead of going to problem 1. Okay, it says a model rocket is launched from the ground with an initial velocity of 60 feet per second. The function, and they tell you what the function is, right here, okay, represents the height of the rocket, g of t, t seconds after it was launched. And they give you a graph that's numbered. Alright, so this is calculator work, guys. I'm going to have, the directions want you to do similar things as I had you add to the ending of this assignment. They want you to find the vertex, they want you to find the intercepts, and they want to talk about domain and range. However, these graphs have domain, or excuse me, have intercepts and vertices that are decimals, and you would have to approximate them if you just looked at the graph. And there's a way to do it on the calculator exactly, especially since the directions tell you round to the nearest hundredth. So we're going to do this on the calculator. So the first thing you really need to do, and I'm going to start with my calculator in its default state. Okay, the first thing I want you to do is set up your window to match your graph. Now the default is to have my x minimum at -10, and this graph also counts out to -10. I know the last number you see is -8, but to make the pictures as close as possible, the calculator shows a picture out to the very last edge. So that would be -10 to +10. So I'm going to leave that the same, and each box, and we're going by boxes, not what the numbers say, each box counts for 1. They just didn't label every box. So I'm going to leave the x scale as 1. Y minimum, okay, the default is -10, but this graph goes down to -100. So I am going to change this to -100. And it counts up to +100. And each box, again, don't go by the numbers per se, because they didn't label every box, they only labeled every other box. Each box counts for 10. Okay, so now when I go to my y equals and I put in my function and I hit graph, it's going to at least somewhat match the picture I see here. Okay, so y equals, and put in -16 x squared plus 60 x. Okay? Now, I want you to do the graph using your table. Table by default starts at 0, but scroll up. Okay, negative to 184. Ooh, my graph doesn't go down to a -184, so I don't need to scroll any far past that, but I can start graphing at -1 and 76, because that fits. So -1 and 76, I'll put a point, 0, 0, 1 and 44, 2 and 56, 3 and 36, 4 and -16, and 5 and -100, and that's all I can fit. So I'm going to stop putting dots now, and then I'm just going to go back and sketch in the parabola. Okay. And labeling is good. Okay, now if I hit graph, I'm also going to turn the coordinates on. Oops. Okay, to turn coordinates on so that you can see the grid lines, I should say, go to your second format. Grid lines on is the third option over here. Okay, now Mrs. Andrews, why does my graph on my calculator look different than the one in the picture? Well, the one in the picture, remember, is a square graph, and the one on your calculator is a rectangle. So if I made this same size and square, then they'd look more alike. But don't see the distortion from the fact that your graph on your paper looks different than the one on your screen. Keep in mind that your screen is rectangle shape and your grids on your homework are square shape. So that makes a difference. Okay. I actually leave that out here just in case I want it. Alright, now what I want you to notice is that, you know, we're supposed to, at this point, say what the vertex is. And in this case, our vertex is a maximum. Okay. Well, I can look at the graph and kind of get an idea of how high the vertex is. But if you look at my graph that I drew and even the calculator one, the vertex is not perfectly on a line. It's not on that 2. Okay. So, unfortunately, we can't just, you know, pick it off the graph and write it down. Our calculator will calculate it for us. It's pretty cool. All right, so what we're going to do is tell the calculator to find the vertex, but we can't have it search through the entire function because the entire function is infinite. We have to tell the calculator about where it's located. So what we're going to do is, if I bring this back up here again, okay, we're going to tell the calculator, hey, the vertex is somewhere in this zone, and we're going to mark 2 things on, we're going to mark 2 spots on here. This is called the left boundary, and that's the right boundary. And we're telling the calculator to look for the vertex in that area only, because that's where it is. Okay? So in your calculator, here's how you do it. Second, calc. Now, it doesn't say vertex, it says maximum or minimum. So in this case, we're doing a maximum because that's what our parabola does. Okay, and then you get a blinky flower here, a blinky X. I think it looks like a flower. And remember how I highlighted that area toward the top? Well, what I'm going to do is take my blinky flower up toward the top. There's not a specific place where you have to put it. You don't have to be OCD about it, although I confess I am kind of a little bit. So get it close to the top, but not all the way. And down here it'll say left bound and a question mark. And you hit enter to say, yes, this is where I want the left boundary to be. Now it's asking for the right boundary. So we're going to go to the right of the vertex. Now, you do not have to go to the exact same spot. It doesn't have to be the same spot on the right as it is on the left. You can be a little high, you can be a little low. It doesn't really matter. Once you get that blinking flower where you want it, hit enter again. Now you see it's marked the graph with 2 vertical lines. That's your left bound and your right bound. Then down here it says guess. Yes, we want the calculator to guess. And guess sounds so inexact, but it's way more exact than us looking at the graph and doing an approximation. Okay, it's out to several decimal points. So we hit enter again, and our boundaries disappear, and our blinky flower is right on the vertex, and it is telling us that the maximum is at 1.8749986. Guys, sometimes those will come out even. Sometimes they'll say 0.999 eventually. Sometimes they'll say 0.0001. Generally speaking, you're going to be rounding anyway. So this the directions say round to the nearest hundredth. So this is going to be 1.87 or 1.88. I've done this a few times, and sometimes that 4 after the 7 comes out of 5. So 1.87 or 1.88 I would have to accept because I've seen it come out different ways each time. Why would it come out different? It depends on where you mark your boundaries, left bound and right bound. When it's doing the calculation, if you put them in a slightly different spot than your neighbor does, you're going to get a slightly different answer, but it's very slight, like 100th difference or 1,000th difference or maybe even less. So then you're not going to get a wide variety of answers compared to, say, a partner. Okay, so 1.87, and I already forgot what it was. 56.25. That is the vertex, and we did not have to approximate that at all. Okay, but we can see that, well, 1.87 is pretty close to 2. Yep. And let's see, 56.25. Yep. Okay, that seems pretty close. Get this stuff gone. Okay, the next thing it wants are the X-intercepts or the zeros. Okay, in this case, we're crossing the x-axis twice. Now, I want to point out in your table, sometimes you can see your zeros. Okay, a 0 is called a 0 because that's what the y value is at that point. Okay, so I look for a y value of 0 and then I see what the x coordinate is, and oh, it's also a 0, but that's a coincidence. Okay, so one of my zeros is 0, 0, and I don't have to do any fancy calculator work to find that. That's where the graph crossed, right on it. But I can see that when it crosses the x-axis on the right-hand side, it crosses somewhere between 3 and 4. And you don't want to guess what that is. We're looking for exact. It says round to the nearest hundredth. All right, now the same series of steps that we did just now on the calculator to find the vertex, we do the same thing to find the zeros. In other words, oh, where'd it go? We are going to tell the calculator to search the graph between, I know that this is where the intercept is, that's where the 0 is. So we're going to tell the calculator to draw those boundary lines here and here, and it's going to search between those two spots on the graph. So let's show you this on the calculator. And it's the same procedure, second calc, but this time we're going to choose 2 for 0. Blinky flower. And we want to be to the left of the 0 for our left boundary. Hit enter. We marked our left boundary. Then we go to the other side. There's our right boundary. And then guess. And it gives us our coordinates, 3.75 and 0. Gosh, I would have said 3.5. So I'm glad that there's a calculator way so that I could get a more precise answer. So 3.75 and 0. Okay. The next thing that the homework wants you to do is talk about domain of the function versus domain of the problem. Okay, so we already talked about the fact that the domain of the graph, the domain of the function, is still all real x. But if we're talking domain of the problem, then we're saying, well, can we really have, say, negative x values? Can we have only positive x values? Will all positive x values be okay? And for here, that we really want to look at the specific situation. Okay, this problem is about a rocket being launched. Okay, so on the domain, remember, is x-axis. So the part of the x-axis on the negative side, nothing's happening to the rocket. Okay, if we go by the graph of the function that goes with this picture, it looks like the rocket's underground. But we know that that's not true. Okay, so prior to the launch, the rocket is sitting on the ground. We're not measuring time at that point. We're really only interested in positive time. So the domain of the problem starts at 0. Okay, starts from the moment we launch the rocket. Then, okay, x values. The rocket is launched, time is going by, and then the rocket lands. And once the rocket lands, the experiment is over. We hit stop on the timer. And we're not talking about any time after that. Because if we look at the picture, it would look like after 3.75 seconds, because that's what this is right here, 3.75. If we go by the picture, it would be saying, oh, the rocket went underground. No, it did not. Okay, at that point, the problem stops. The function would graph forever, but the problem stops at 3.75. Okay, gosh, those numbers look awfully familiar. Yes, they do. They are related to your intercepts. Okay, they are related to your intercepts. Okay, range. Just like before, the range of the graph, I gotta be specific here, the range of the graph is related to my vertex. The y value, ranges are y values, it's related to that. This parabola opens down, so this is y less than or equal to 56.25. I should say all real. Okay. However, the range of the problem. Okay, and here's where common sense comes into play, guys. Okay? The rocket was never underground. We're not interested in any y values where the rocket was underground. So our y values start at 0. Okay? So then the rocket takes off and goes up. How high does it go up? It goes up to that 56.25. And that is the range of my problem. Okay, so there's a difference between the graph and the problem. Okay, the graph is a function of is a picture of all the possible points from putting in that function into our y equals. But because this is about a rocket, we may not be interested in every point. We may just be interested in the domain and range of the actual problem, which doesn't include negative numbers for either domain or range. And for the x value, we're limited to our zeros, and to our y values are limited by that vertex point, that maximum height of the rocket. Okay. One more thing for your quiz tomorrow. Hope if you're still with me, it's a good little help for your quiz tomorrow. Your quiz tomorrow will have a problem on it that looks something like this. And it's going to say put that in standard form. Standard form is ax squared plus bx plus c. So standard form is ax squared plus bx plus c. And you might be saying to yourself, Miss Andrews, quadratics are supposed to have a squared in it. I don't see a squared. Okay, if you distribute 2x times 5x would be 10x squared, because x times x would be x squared. Minus 2x times minus 7 would be minus 14x. Bring down our plus 4, and there's our function in standard form. So it's just a reminder on distributing. Okay? One last thing. Sometimes you can see things like zeros and vertex right in the table. Sometimes. Okay? If you have a y value that's 0, that's your x-intercept. The x value doesn't have to be 0. Okay? But you can see it right in the table. Down here, I have a y value of 0. So this is an x-intercept. at 10, 0. Okay. I can also, in this table, I can also see the vertex. I can see the number where I'm going up, going up, going up, going up to 400, and then I start going back down again. So my vertex is at 5, 400. Now, there's a specific reason why this works in this case, but it won't happen in every quadratic. Don't just assume that the highest or lowest y value in your table is going to be the vertex, because it won't be unless it does this. Notice how I have 384 above and 384 beneath. 336, 336. 256, 256. 144, 144. And 0 and 0. Okay, when your y values in your table do that, then it is safe to say that the highest or lowest y value is your vertex, is your maximum or minimum. But it does not always happen. Let me show you. Okay, this is another quadratic set of data. I can see 1, 0. Okay, I can see 1, 0 is here as 0, 0. The other 0 I can't see. Okay, because there's no y value of 0. It was positive at 36, now it's negative. I can't see the other 0, and what that tells me is that my 0 is 3 point something. Okay, so I can't see the 0 this time. All right, also 56 is my highest value, but it is not the vertex. Okay, how do I know it's not? Because 44 and 36 don't match. Negative 16 and 0 don't match. Negative 100 and negative 76 don't match. So what's that tell me? It tells me that the vertex has an x value that is not a whole number, and I'm going to have to go in my calculator and do the right bound left bound thing if I want to find it. Okay, thank you for staying with me. This has been a long video. Have a good day. See you next time.